Motor buses are an indispensable transport resource in city traffic and for overland transport. High demands on safety apply to them. Periodic technical inspection of vehicles contributes to ensuring the conformity with specifications of motor buses and thus the maintenance of traffic safety. Special features and required testing steps for the different types of motor buses are documented by the FSD. FSD HU21 serves as an information source and reference for testing. The application and sequence of the testing are at the responsibility of the expert. In this film, the main focus is on the following: visual inspection, testing of the electronic brake system, performance testing of the brakes, testing of the adaptive cruise control, testing of the starting prevention device, special features of articulated buses, and overview of future challenges in vehicle inspection. Truck and motor bus are considerably differentiated in regard to body structure. As well as the ladder frame design, which is applied in truck design, the self-supporting body is often employed in the motor bus. In this case, it involves a grating tubular frame or a combination of ladder-type frames and grating tubular frames. Only a proper condition of all supporting parts guarantees the stability of the body. All longitudinal and cross members, the frame, the axle connections and also the bonded-in window panes must be functional. Special attention is paid to the connecting points of running gear and body. Huge forces act on the fastening points of the anti-roll bars. In particular, attention must be paid to deformations at the force application points as well as cracks. A displacement of the bearing elements indicates excessive wear. In the course of the visual inspection of all structural parts under the vehicle, the steering is also examined. The tie and connecting rods are examined for play, freedom of movement, fixing and damage of the sealing in this case. In the same way, deformations of the steering rods can be identified. The control check of all lines running underneath the vehicle for fixing, deformation and sealing is also included in the periodic technical inspection. In case of pipework below the vehicle, the danger exists that this can be deformed or even torn off due to impacts with objects on the road. Also, any damage to the fastening points of the fuel tank can lead to dangerous situations. The position of the NEVO sensor of the electronic air suspension represents a measure of the loading status of the vehicle. In case of deformation, they supply incorrect values to the control unit, which can lead to unstable driving characteristics. Prerequisite for trouble-free functioning of the electronic air suspension are air spring bellows, which are neither damaged nor worn. The protection of the swivel coupling, as well as all supply lines of the tail car, is the task of the flexible bellows. The permissible overall weight of an articulated bus can be up to 28 tons. The dead weight itself is already a good 18 tons. Therefore, jacking up the bus is possible only at the jacking points provided for that. The visual inspection of these jacking points for cracks and deformation should be carried out systematically. The engine compartment is to be examined for possible damage. In case of a fire in the engine compartment, the walls must be capable of suppressing the fire until an evacuation of the passengers has been carried out as quickly as possible. Motor buses must meet special requirements in regard to their equipment. During the periodic technical inspection, additional test steps are therefore necessary. The window panes are a factor not to be underestimated in the structure of a self-supporting body. Defective window panes impair the stability of the body of the bus and must therefore be examined for cracks and fastening defects. The pneumatic brake system forms the basis for the electronic brake system. The manufacturer-specific special features of the brake system are made available to the inspector by the FSD. Within the framework of the periodic vehicle inspection, a function test of the pressure protection is to be carried out. In this case, the security of the service braking system is tested with respect to each other and secondary consumers. In addition, the security of the secondary consumers is tested with respect to the service brake circuits. If, for example, a pressure loss occurs in the service brake circuit, the other circuits must be stabilized at the security pressure. If the vehicle with the defective service brake circuit should no longer achieve any residual braking effect, and if the parking brake is additionally activated at standstill, the vehicle must be prevented from driving off. A possibility of satisfying this requirement is the time-delayed venting of circuit 3 over a bypass. A further possibility is also the so-called parking brake interlocking. During driving, however, the spring-loaded units may not react automatically, since this can result in the blocking of the back wheels, which would result in unstable driving. For this reason, the designated functionality is to be tested. The vehicle is prevented from driving off until the reservoir pressure is again present at a sufficient level in order to achieve the residual braking effect. If the spring-loaded units are engaged and circuit 3 is pressure-free, it must be nevertheless possible to remove the vehicle from the danger zone. In commercial vehicles, it is possible to tighten the spring-loaded units mechanically at the multi-purpose brake cylinders, which is difficult in the case of motor buses for reasons of space. Therefore, pneumatic emergency release equipment fed from circuit 4 is often used here. In modern pneumatic supply units of different manufacturers, compressed air supply, pressure regulator, air dryer, multi-circuit protection valve, pressure control valves and electronic controls are combined into one mechatronic unit. As a result of an intelligent pressure regulator control combined with a special air drying process, this unit offers the advantages, in comparison to previous compressed air supplies, of less fuel consumption, monitoring of the air preparation over the CAN bus, and cost savings in maintenance. As well as the initialization and the test drive, the testing of the EBS also includes the visual inspection of all significant component parts, such as wheel rotational speed sensors, cable and plug connections, yaw rate sensor, braking value transmitter, brake modulators, etc. With the initialization and the subsequent test drive, the programmed functions such as the automatic anti-lock braking system, the electronic braking force distribution, the traction control, the electronic stability program, the drive-off assistant back rolling block, the braking assistant and the engine pulling torque regulation of the brake control unit are tested in self-diagnostics. It is certainly possible that the ABS light first goes out with the test drive and with a speed greater than 10 km per hour. The system prevents the wheels locking during braking by means of an appropriate decrease of the wheel braking force. In case of an icy or slippery roadway, such as ice, snow or leaves, in case of braking with the same braking force on all wheels, the wheel on the road with the least coefficient of friction will lock. By means of the wheel rotational speed sensors, the ABS evaluates the rotational speed of the individual wheel and decreases the braking pressure of the more slowly rotating wheel. In addition, all endurance brakes are switched off in case of ABS interference. The braking force distribution regulates the braking pressure at the rear axle according to the operating conditions. In driving operation, the rear axle is unloaded in case of every braking action and as a result tends more to locking than the front axle. With the aid of the rotation speed sensors, the least rotation speed differences of the axles are determined. If a difference exists, the braking pressure at the rear axle is reduced to such an extent that the same rotation speed of the two axles is reached again. Any possible overbraking of the rear axle is prevented by this. The function traction control prevents the slipping of the drive wheels by decreasing the engine torque and braking application on acceleration. On roads with low coefficient of friction, slippage of the drive wheels should not occur. With the aid of the wheel rotational speed sensors, the traction control determines the rotational speed of the wheels of the driving axle and compares this to the reference speed of the vehicle. Any slipping of the drive wheels is prevented by decreasing the engine torque and/or appropriate braking application. With the ESP, the vehicle is stabilized in drive dynamic critical situations by means of engine and brake intervention. For example, the engine torque is reduced in case of a too high speed when cornering, and the brakes are activated on certain wheels. In this way, the ESP prevents oversteer breakout of the vehicle in the curve. The braking assistant supports the driver in emergency braking. After evaluation of the actuation speed of the brake pedal by the brake control unit, the full braking pressure is applied to the wheel brakes independently of the pedal position. The ABS prevents any possible locking of the wheels in this case. In case of a sudden load change or fast gear change down, the drag torque of the engine is increased. This can lead to the locking of the drive wheels and to unstable driving characteristics. In order to avoid this, the rotation speed of the motor is increased through the engine drag torque regulation and any locking of the drive wheels is avoided. The evaluation of the signals of the wheel rotational speed sensors is the initiation point for this regulation. With the back rolling block drive-off assistant, the braking force is retained at the wheels for a short period after release of the brake pedal in order to prevent any rolling back when driving off. For this, the starting torque is tested with respect to the braking pressure. In case of automatic transmission, the braking pressure is maintained for approximately 2 seconds after release of the brake pedal. In case of manual transmission, the brakes are released only after reaching a predetermined driving torque. The braking forces are measured as previously together with the relevant braking pressures as a reference value. The inspector applies a pressure with the brake pedal up to a value just before wheels lock. The braking forces and braking pressures determined are compared with the reference values. The reference values are provided in tabular form, vehicle and axle related. With the reference values, a more precise evaluation of the effectiveness of the operational brakes is enabled for the inspector. The comparison of the measured braking forces with the reference values can also be implemented automatically in future using software, such as, for example, the FSD suite or the respective production application. The printout of table values is no longer necessary. The recording of the measured braking forces can also be implemented automatically in the near future. The interface of the brake test stand transfers the data, which is currently being determined at the test stand, such as braking force, slippage and speed, as well as optionally braking pressure, pedal force and wheel weight to the PC of the inspector over a standardized data interface. The braking forces are evaluated automatically and can be entered into the test report. As well as the function of the cruise control to maintain a specified speed, the distance to the vehicle ahead can also be kept constant with the Adaptive Cruise Control System, ACC. The traffic situation in front of the vehicle is monitored by means of environment sensor technology. If a vehicle ahead is registered, the pre-selected distance is adjusted where the driving speed is adapted by the ACC. For this purpose, the engine torque is decreased and the brakes are control activated. The driver is informed about the interference in the display. As soon as the vehicle ahead has left the sensor range or the driver has the possibility of overtaking, the ACC accelerates automatically to the pre-adjusted speed. An extension of the ACC is represented by the Automatic Emergency Brake System, AEBS. As well as the functions of the ACC, it also offers the possibility of automatic deceleration of the vehicle in a dangerous situation. If the environment sensor technology identifies a vehicle traveling slowly, example giving at the back of a traffic jam ahead, then the driver is first warned optically and acoustically. If the driver does not react by braking or steering appropriately, an autonomous partial braking is initially implemented. If the driver still does not react, full braking is applied. The environment sensor technology is the central module assembly of the Adaptive Cruise Control, ACC, and the Emergency Brake System, AEBS. These sensors installed in the vehicle front may not be covered or damaged. In case of some vehicles, an evaluation of the measured values of the environment sensor technology is possible. For this purpose, the distance of the vehicle to a non-moving obstacle is changed, and the relative movement compared with the output sensor values. Also, all system-related control units and operating elements must work without error. An automatic unit which prevents the driving off of the vehicle from standstill is referred to as a starting prevention device. The installation of this component is optional. If the installation is determined during testing, the corresponding test specification is to be employed dependent on the first registration date. In case of motor buses first registered after date 13th of February 2005, the following points are tested. If a starting prevention device is installed, this may be effective only at speeds of less than 5 km per hour and must be inoperable at speeds above that. If no starting prevention device is installed, a sound audible to the driver must be emitted if the vehicle drives off from standstill, and an externally activated operating door is not completely closed. This sound must be emitted at a speed of more than 5 km per hour. In case of motor buses first registered before date 13th of February 2005, the following checkpoints apply. The starting prevention device block may act only at driving speeds below 5 km per hour. A release of the starting prevention device may be implemented only after closing the doors and with subsequent depression of the accelerator. The starting prevention device must also remain closed in case of interruption of the ignition current, as long as the parking brake has not been applied. In case of interrupted ignition and parking brake not applied, an acoustic warning must be sounded. Starting prevention devices must be disconnectable in an emergency. The switch is to be structurally arranged in the grip area of the driver. The disconnection of the starting prevention device is to be displayed self-explanatory to the driver. There exist articulated buses with a drivetrain in the front vehicle and those with a drivetrain in the articulated vehicle. With front vehicle drivetrain, the rear car is pulled. The driving characteristics correspond to the tractor principle with drawbar trailer. With the concept of the drivetrain in the articulated vehicle, a pushed articulation joint is employed for drive dynamic stabilization. The pushed articulation joint is a swivel coupling which is capable of being continuously damped. In some cases, a damped articulated link is also installed in case of pulled rear car for train stabilization and to increase comfort. The articulated links are provided in different design implementations. The pushed articulation joint stabilization is a drive dynamic system with intervention in the steering system. The system adapts the damping of the articulated link according to the driving situation and input data. The solenoid valves of the hydraulic dampers are control activated for this purpose. In case of maximum bend angle, the articulated link is 100% damped, so that no further pivoting between the front and rear cars is possible. The bend protection prevents any contact of front and rear cars in order to avoid any mechanical destruction of the structure. The system works only at low speeds. In case of a critical bend angle, an acoustic warning is emitted to the driver. In case of backwards travel and exceeding the critical bend angle, the bus stop brake is additionally activated. Both functions require, among other things, the following input signals: the vehicle's speed from the tachograph or instrument panel, the bend angle from the bending angle sensor, and the direction of driving from the transmission. The following defects can occur in pushed articulation joint. The articulated links and the suspensions can be worn out. The cylinder can be worn and leaky. The centralized chassis lubrication can be without function. The bending angle sensor can supply no values or incorrect values. The power supply is interrupted and the emergency function is activated with a defined level of damping. According to accident statistics, buses are the safest vehicles on the road. In spite of that, serious accidents still happen with buses, which usually result in suffering for a lot of people. So that accident victims in buses suffer less frequently in future, driver assistance systems should be installed as quickly as possible in all new buses, which will actively intervene in the driving dynamics and therefore help to avoid and reduce accident consequences. Experts, with their know-how and their modern testing technology, will contribute to ensuring that these accident avoidance systems are kept functional over the entire vehicle lifetime of a bus. The efforts will be worth it, and the vision of accident-free driving with buses will increasingly become reality.
Thank you.